Okay, so today we're going to discuss how to compute the derivative of a vector field along a curve. So let var be a smooth map, from an open subset U of Euclidean space Rn into a larger ambient space R capital N, which is an injective immersion. So injective meaning that it's one-to-one, and immersion meaning that the Jacobian or the differential is injective at every point on the domain. Now the image of var is our manifold M, okay? And, um, and now let's look at the Jacobian matrix. Since we have a canonical coordinates on our domain and codomain, we're assuming we have canonical coordinates, and these coordinates I'm denoting by x for the domain and y for the codomain. We can build the Jacobian matrix. And by our assumption that this var is an immersion, Jacobian matrix must be injective at every point in U, okay? So this Jacobian matrix, here it is. The point x is given by the partial derivative of the ith component of var with respect to the jth coordinate in the domain, okay? Partial var over partial xj. Now, the column vectors of this Jacobian are going to be um, given by in our coordinates y for our canonical coordinates y for the codomain. They're given by the following expression, whose coefficients are just the partial var I over partial xj, where I runs through the components of the vector. Okay, so I is running through the components of the vector. And then we have a set of lowercase n basis vectors, which form a basis for our tangent space. Now, the reason why these vectors form a basis is, again, because this Jacobian matrix is assumed to be injective. So these will form a basis of the tangent space to the manifold at var of x for all x in our domain. Okay? All right. So that being said, we're now going to introduce some notation, some compact notation. So at a point y, on our manifold, okay, now I didn't write this down, but y needs to belong to the manifold M. Then we're going to denote this basis, the elements of this basis for a tangent space. We're just going to denote them by phi subscript j. Now, notice that I'm using the Einstein summation convention here. So for those of you who don't know, the Einstein summation convention means that repeated indices are summed over. So in this case, this expression is summed over I, and then notice how the coefficients of this basis vector are evaluated at var phi inverse of y, because these coefficients, right, these partial derivatives, partial var phi I over partial xj, these need to be evaluated at a point on the domain. So we need to um, actually take the inverse of var phi in order to evaluate these coefficients. And then, of course, this partial over partial yi, this is just the canonical frame for the codomain. Okay. So now we're going to let mu be a curve. So a curve parameterized on the interval I into our domain. Okay. We're taking a curve in our domain mu, and we're going to define gamma to be the image of this curve under the embedding map var phi. So yeah, so we define gamma here to be var phi composed with mu, and that's a curve in our manifold. Now, once we have this curve in our manifold, we're going to let this x of y be a vector field along this curve. Okay, so when we say along the curve, we mean that this vector field belongs to the tangent bundle to M. So at every point y, this vector field can be expressed in terms of the basis var phi sub k of our tangent space to our manifold. Okay, so these coefficients of the vector field are this x subscript or superscript k, and the basis vectors are var phi subscript k. Okay, And here I've written a summation symbol. That's the only time I'm going to write the summation symbol. And in general, I'm just going to use the Einstein summation convention. Okay. All right. So the question that we have for today, is, okay, so we have this vector field, which is along our curve gamma, and we know that gamma is actually parameterized in this coordinate t, which depends on the parameterization of our curve mu. So this induces a parameterization of the vector field. And namely, we just evaluate, of course, in the obvious way, x of t is just the components of x evaluated at gamma of t, and then the basis vector is evaluated at gamma of t. Okay? And we wish to find the derivative of this vector field with respect to t. All right? So I'll let you pause the video and try to solve this on your own. Try to see if you can find the derivative of this vector field with respect to t. Now, the important thing here is that if this were a vector field expressed in the canonical Euclidean frame, then we would only have to find the derivative of the components. Because the canonical Euclidean frame, namely in our codomain, the canonical Euclidean frame is given by these vectors here, okay, this partial over partial yi. The canonical Euclidean frame is constant at every point in Euclidean space. And so to take the derivative of vector field expressed in the Euclidean frame, you just need to take the derivative of the components. However, in this setting, our frame for the tangent space of the manifold depends on our location. So this vector frame is changing as we change t. Okay, and so that's going to introduce a complication when we try to find this derivative. Okay, so let's go ahead and compute the derivative. Now, first we need to set up some preliminary calculations. Okay, so I need to to take this derivative, I'm going to have to use the product rule. I'm going to have to take the derivative of the first times the second plus the derivative of the second times the first. And so I'm going to actually just compute these derivatives explicitly before I go ahead and take the full derivative of the vector field. Okay, so let's look first and foremost at the more complicated term, the basis vector itself. So we look at var phi sub k. This is our basis vector, and I rewrote this basis vector, but now I evaluated it at gamma of t. Okay, so remember that the components are evaluated in the domain, and so the components of this var phi sub k are going to be evaluated at mu of t, which is actually nice. That's a simplification. Okay, and then the basis vectors partial over partial yi are evaluated at gamma of t. All right. So I mean this first expression just follows immediately. If we go back to our definition of the basis vectors for the tangent space, we can see that when you plug in gamma of t for y here, remember gamma of t is var phi composed with mu. We plug in gamma of t for this y here, the var phi inverse will cancel with the var phi, and we're just left with a mu of t evaluated in our components. Okay. All right. So that's the first expression here. And now let's take the derivative of this expression. And so to do that, we need to look at this term here and ask ourselves, well, what actually, like, this component term here, this is a map from some space to some space. So we know that the component var phi I, the component of the embedding, the ith component of the embedding, I'm sorry, it keeps refocusing. So the ith component of the embedding is a map from our domain into the real numbers. If we take the partial derivative with respect to the kth coordinate of the domain, that still gives us a map from Rn into R. Okay, so since this component is a map from Rn to R, then when we take its derivative is just going to be applying the chain rule. We're going to take the gradient of this function and then dot that with mu prime of t. And so that's this expression here. This is precisely the gradient of this function in the x coordinates dotted with the derivative of mu of t, where mu superscript alpha is the alpha component of mu in the x coordinates. So this is just the gradient of this function dotted with the vector mu prime, okay? And then notice that the basis vectors just stay constant, because this, in our codomain, this is a constant. This is the nice thing, it's a constant frame for Euclidean space. So this actually is not changing with respect to t. And so when we take this time derivative, we only need to take the derivative of the component, okay? Now, let's look at the coefficient of the vector field, okay? So the coefficient of the vector field is a map from the codomain into the real numbers, okay? So when we take its derivative with respect to gamma of t, we're going to have to invoke the chain rule, okay? So to do this, we're gonna basically, this is the first step, is the chain rule. So we have the differential of this component, which is just going to be its gradient, and then it's going to be applied to the vector d gamma over dt. Now remember, gamma itself is a composition of functions. Gamma is equal to var phi composed with mu. So when we take this d gamma over dt, we need to use the chain rule again, and then we take the differential of var phi applied to the vector d mu over dt. Okay. All right, wonderful. So when we apply this, this is just the Jacobian matrix, and we're going to apply the Jacobian to this vector d mu over dt. And since the column vectors of this Jacobian matrix are just our basis vectors var phi subscript c here, then this matrix multiplication is just going to end up being the coefficients of this vector um, multiplied by the column vectors, and then you sum over the column vectors. Okay, so that's just matrix multiplication. And then now we evaluate. Now we have this expression. Now we have like an explicit form of this vector that we're trying to apply this differential to. But I want to actually unpack this a little bit further. I want to get this vector in terms of the Euclidean frame, the Euclidean basis. So that's just one more step of unpacking this, again, using the definition of this basis vector, right? If we go back one more time to this definition of the basis vector, right? It's just again, I'm not going to repeat it, but that's the definition of the basis vector. So applying that definition, we can express this vector in terms of the Euclidean basis, and these are the coefficients here, summed over c, okay? And so now we can just go ahead and take this differential. Now this is just, again, this coefficient function is a function from Euclidean space, the ambient Euclidean space of the codomain, into the real numbers. And so to apply this, this coefficient, due to linearity, this coefficient just pops out here, and then we just apply this differential to the basis direction, and that is just going to be literally the lth component of the gradient of this function. So it's the lth component of the gradient of this function. That's precisely this term here, partial xk over partial y l. Okay, and then we're going to simplify this notationally. We're going to simplify this expression according to the lecture notes by Wang. By the way, this is all following the lecture notes by Wang. These lecture notes by Wang. I'll post a link in the description, but this is where I'm getting all of this information from. So now, according to Wang's convention, we're going to write this in a simplified form as this term here, where we essentially have this partial over partial xc, the partial of var phi superscript l over partial xc, partial xk over partial yl. This summed over L, we're going to rewrite this as just partial subscript c, okay? And yeah, that's just a notational convention to simplify the calculation, okay? So now we have the pieces that we need to go ahead and compute the derivative of the vector field, all right? So So we begin with our expression for our vector field. We take the derivative. The first step is just going to be the product rule. And then, as you can see here, we have the derivative of the component times the basis vector plus the component times the derivative of the basis vector. Okay? And now I'm just going to plug in what I already explained previously to calculate. I calculated this term, the derivative of the component, and I also calculated the derivative of the basis vector. So I'm just going to plug those in right here. Okay? All right. Now, the important thing here, okay, so let's unpack this next term. Okay? So again, this is a second derivative of the component function with respect to alpha, and then, or with respect to k and then alpha. So this second derivative, okay, term is showing up in the derivative basis vector. We have a second derivative of the component function, and this is summed over the basis for our codomain. Now notice that this summation is still in terms of the Euclidean basis for the codomain, whereas here we have an expression. In the first term, we have an expression that's already written in the basis that we like. It's already written in the basis for the tangent space, this var phi sub k. But the second term is still written in terms of the basis for the ambient Euclidean space. So ultimately, we want to project this term onto the tangent space, all right? And the way we do that is by using the Christoffel. Well, okay, that's just, you can always project a vector onto a vector subspace using linear algebra, okay? And so the Christoffel symbols, by definition, are the coefficients of this vector here. So this vector, again, that I was kind of emphasizing, the second derivative of the component, the ith component function with respect to k and then beta. And by the way, these partial derivatives commute in the Euclidean setting, so it doesn't actually matter the order, summed over I. So we project this vector onto the basis for the tangent space, and that gives us this linear combination of basis vectors for our tangent space, and the coefficients of this linear combination are the Christoffel symbols. Okay, and then the remaining term, this h subscript beta k, is just the projection of this vector onto the orthogonal complement of the tangent space. Okay, now, so I'm going to recall that real quickly. This h beta k is the projection of this phi beta k term, which is, phi beta k is just basically the efficient notation for this expression. Okay, so the projection of this expression onto the orthogonal complement of the tangent space, this is defined by our h beta k, right? And this is actually the coefficient matrix of what's called the second fundamental form. But I'm not going to go too much into that now because I want to finish this video. So, okay, so we have this, basically this second order term, second derivative term, and we've projected it onto the tangent space and then taken off the piece which is on the orthogonal complement of the tangent space. All right, and so now we can just plug that in to our expression. We plug that in directly, and what we get is the following expression. So we want to isolate for the coefficients of this vector. This is the derivative of the vector field with respect to t. We isolate for the components with our basis var phi sub L. Okay, so I fix the index of the var phi in both of these expressions, fix the index of the var phi, and just factor out the component of both terms, and you get this expression. So derivative of mu superscript xi with respect to t, and then summed over the partial xi of the components of the vector field. Okay, and then we add the component of the vector field, this Christoffel symbol, lambda L beta k, and then the derivative mu beta over dt here. I'm sorry if I'm not there's a lot of indices going around, so it's kind of hard to like translate this math into an English form. If you have any tips on like how I can better communicate this through the English language, please let me know, because there's a lot of index juggling here, and it's very algebraic, it's very computational. It's hard to really see the deeper meaning of this, but I'm also just learning the subject. So yeah, any comments or criticisms are super welcome. Okay, so we've isolated for the term of this derivative, which belongs to the tangent space, and we've isolated for the components with respect to our basis var phi sub l of the tangent space. And then we have this remaining term, which is belonging to the orthogonal complement of the tangent space here. So this is x superscript k, h beta k, d mu beta over dt, all right? And this term here, this term which is the projection onto the tangent space, this is what's called the covariant derivative, okay? So yeah, this was a very hard video for me to make. It's partially due to my inexperience with the subject. It's kind of hard for me to communicate it to it, but hopefully the computations made sense. And yeah, let me know. Please give me some feedback as to how I could better explain this, or if you have any intuition, some more intuition, some geometric intuition, maybe about the definition of this partial sub c. If we go back to how it was defined over here, we have the partial sub c is equal to this term where we're summing over L, okay? So this is somehow like a derivative with respect to the, if you view like var phi as like coordinates on your manifold, this is somehow this can be like represented as like the derivative, um, the coordinate wise derivative in the like in the in the direction of, if you view the var phi as like coordinates, then basically we take the the x sub c coordinate of our domain, so that's like a horizontal line, let's say a line in our domain, that gets mapped via var phi to some curve in our codomain, which we can think of as like a coordinate in the codomain, and this is like the derivative of the component of the vector field in that direction, you could say, okay? So that's how I currently understand this expression here, um, and and yeah, so it's easy to get lost. I feel like I am getting a little bit lost in just the notation and all the all the symbols, all the different coefficients that are getting juggled around here. So yeah, any comments would be greatly appreciated, and hope you all have a great day.